how that dynamics. So on its 4 feet, just of this. Dynamics means the evolution in time. As the time progress, something evolves. Okay, and it can be periodic, it can be non-periodic, it can be anything. So it can be chaotic. So there could be many responses to it, but uh, depending on the system characteristics, we have to first analyze the system. So what we do, we make a mathematical model out of it. So how can you create a mathematical model? Is first you have to look at the abstraction. So without going into much theory, we will just start with a practical problem involving a cat. So just a question, if I throw a cat like this, what do you think? Will it land on its 2 feet or 4 feet, or it will just die? So options, let me put the options. Option 1 is cat will die because of fall. Option 2 is cat will land on its 4 feet. Option 3, either cat will scratch you. Can anybody so if I, the question is, if I throw a cat like this, like, okay, let's correlate with a human example. If we throw a human like this from a building, will that human will be able to land on its 2 feet? You can put on the chat also. No, right? But the cat has a unique ability of scratching you and landing on your it on its 4 feet. How did a cat do that thing? Now we should ask this cat. So it got revealed by studying the motion of the cat, and then it was about, because we have seen cat falling from 9th floor, 10th floor, and still it's landing on its 4 feet. Something extraordinary thing is there in cat which we obviously don't have. So actually, can cat move their front and hind limb independently of each other? So there are some special powers in CAD which they can do, and which enables them to adjust their limb position, and in that way they can control their orientation from the fall. So it's like if you release a cat, it will first detect how much height it's released from, then it will slowly move its body somehow to so that it will land on its 4 feet. So here are some major points. So there are different stages of it. Stage 1 is what I called it detection. Don't worry, we are not going into any math part of it. We will be just solving this problem in very technical jargon term. We are not going into any math. It's just we are making a mathematical model out of physical model. So when the cat detects the detection, it kind of first detect how much height it is from the floor, and then it has an automatic response. And what are this automatic response is given by the successive other stages. Now stage 2 is where it arcs its back. So as you can see, it makes a curved it makes a curvature. Okay, so it's an arcing of a back, and this arcing initiates the twisting movement. Now you see that in this let's say the infographic as well as the real photo, it's not exactly the same, but obviously the cat expression are different, but you can see that how the body changes its orientation. So in the second figure, the legs and whether the hind legs and the front legs both are getting into different direction. Okay, so this is called twisting. As we twist our back like this, okay, so their leg as well as upper body part twist in different direction, just like a yoga. So that is the first thing, bending and torsion. Okay. Next, what it does. So once that bending is done or the torsion is done, actually it is both, because it arcs its back and then it twists. So it's like arcing it back and then twisting it. So it allows the cat to rotate its upper body in the opposite direction to its lower body. Okay. So still we haven't figured out how. So still just the upper body part is now aligned to the floor. Okay, but lower body part is still there. Now what it does, it extends its paw like this, and now what happens, that two things happen. One thing, the extending of this thing gives the cat a control of how much to rotate. If it's very far down there, so it will just slowly extend its limbs, front limbs, and if it's very near, then it will quickly extend its limbs. So it gives us the control. Okay, so when it extends its front leg outward, it helps to slow down the rotation. So that is very important. So this is the main reason of the cat being confident enough of just falling from the floors. And also, when the cat is extending its limb, what is happening, that the air resistance which the cat is getting, that will also increase. So it will also slow down the cat. So both these points are very beneficial to cat in slowing down as well as having a control over the rotation. So that is stage 3 now. Stage 3 is flexing of the front limbs. Okay, now what happens? Okay, so still the back part is rotatory in the different direction, as you can see here. Okay, so how this thing comes down is by extending the hind legs. So when the hind legs are extended, it's like you're stretching your feet. Okay, when cat does that in this orientation, when it stretches its leg, then what happens, that there is an automatic twist, because already we introduced some twist in the whole system. So it's like you are floating in the space and you wanted to go from one point to another point. Okay, and you have a ball with you, so you just release the ball into one direction, you will go into the opposite direction. Okay, similar thing happens with the cat, where it rotates in its body, the upper body, and it stores energy. And when there is a point of release, so that it comes to the orientation, then it will reverse it back, like it will store energy and then release energy. So stage 4 is all about releasing the energy. So what are the steps? It flexes its hind legs. Okay, due to that, what happens, there is a follow back twist or bending, and then all the limbs are in now downward direction, and the cat is now ready to land, just like our Chandrayaan 3. So now the question was about developing a abstraction. Now still we haven't found the mathematical model, right? So we have to find that mathematical model. There's a disclaimer, please don't do this at home. While that self-writing increases the cat chances, but obviously there is a chance of cat dying. Okay, so option A is also correct here. Cat can die also. So please don't do this at home. Okay, so starting with our abstraction, first, always the abstraction, when we are converting a physical model into a mathematical model, we always have a purpose. So what is the purpose of this abstraction? It would have been that how cat jumps. Okay, then I would have used some other model, but here it's about the super cat ability to land its on 4 feet while falling down. So the purpose of abstraction here is the study of movement, and that movement is when cat lands its feet first while falling. Okay, so a short model can be made in a control algorithm, that there is some sensing equipments, and those sensing equipment just sense the orientation. So how much the orientation is, if that orientation is very much disturbed, then how to control it. The second part is controlling an actuating element. So the controller is connected to actuators, and that gives us all the legs in the downward direction. So that gives the output. So hence this is the automatic response. Okay, so this is the first cut abstraction model, in which we can say that we can, let's have a sensor on the, let's say, cat's back, or the abstraction we are making. So it's just like making a robot, a cat robot, where it can do this function. Okay, so that robot, when it's released from a height, that robot is capable of reading that how much height it is. So we have a lot of sensors, so we can use those sensors. And then a very simple sensor is, I will just give you an example. So you put a jam on a bread, okay, and tie on the cat's back, and just leave the cat like this. So to prevent that jam to prevent that jam to stuck on this floor, so what cat can do is flip okay, and that is the flipping what is happening. So this is a simple sensor design which we can do. So that will give us the basic equipment of stage 1 and stage 6. Stage 1 is detection, stage 5 is landing. But the major thing which is happening is in these stages: stage 2, stage 3, stage 4. So we will talk more about that. So first of all, is it 3D model or 2D model? So this is 3D model because the CAD is rotating as well as bending, okay, and it is also flexing. So three motions are there: bending, torsion, and actually deformable bodies. So abstraction should be in 3D. So a simple abstraction I have made like this. So there are two cylinder or major body part, and it is connected by some element. So this is bending torsion element, and all these are joined by hinge, okay, and it is actuated. So it can be rotated in some sort of manner. In reality, the tail plays a very much very high role in this phenomena, but as of now we are just neglecting the tail, okay. Actually tail is the main actuator in the cat's body, but for now we will just neglect it. Now stage 2 is where it was bending. So now how it is doing like that is that deformable body or bending torsion body, it can rotate or it can twist as well as bend, okay. So that's what is happening. And if you fix the back side of it, like because the cat backside is same as the first figure, so hence there is only rotation in the first figure. So hence what happened that there is a bending as well as torsion into the system, and it is kind of energy stored, okay. So this is energy being stored into the spine, and then there was a forehind extension. So when it did that extension thing, there is a control over rotation, okay, and also there was a air resistance. So when there was a air resistance, what happened that it slowed down and it has a control over the rotation. So cat know that how much extension it can provide, right, and how much slowly it had to move. So it had to first perceive the distance and then it had to move like that. Then final part, which is the most magical part of the whole scenario, is rear leg extension. So when it extended its rear leg, what happened that there is a follow back twist. So just imagine cantilever beam being into like this, and it is like twisted also, and just you release those twists, what happens that it will come back to its sweep position. So that is what is happening. So when it flexes its leg, the hind leg, it kind of create a effect, which a domino effect, which kind of gives the follow back movement, and that is the moment where two out of its four limbs, it comes to the downward position. So hence it lands. So today you know how a cat land from a very high buildings to ground and still they are alive. Okay. Moving to, so let me label the question number 1. So any doubt till now, you can write in the chat window, or you can ask me directly. This is the dynamics of the cat. Okay. Okay, second question is again about something biological. So let's say there is a CD drive and it is rotating at very high speed, uh, and it has angular acceleration of alpha. Okay, now this ant is moving from point A to B in a straight line. So this disk is moving, and also A and B points are also moving. So what we have to do is we have to imagine a realistic situation. So this is tricky part of the question, and also the non-mathematical part. So where you have to imagine a realistic scenario, like how many degree of freedom do you need to describe this ant motion. So to define what a degree of freedom is, how many independent coordinates are required to describe the motion of this ant? Any idea? So you have to think like a practical person. Don't look at the question itself as a question, which is our competitive exam structure where we just try to solve the problem. But you have to think practically. You have to feel like an ant. Assume yourself being an ant and you are on a very large disk rotating at very high speed, okay, and it's increasing in the speed because there is angular acceleration. So that means that it is increasing by, so omega is equal to alpha t. Omega is the speed of rotation, and as the time progresses this alpha t becomes more and more, okay. So this omega becomes more and more. So just imagine yourself being walking in a straight line in a very rotating, high rotating disk. What will you feel? Okay, this is question about that. Any comments? Okay, so I will go to the solution now. Okay, so anyone, any answer, or you can explain the situation also. The answer of this question is not related to physics or maths. It's a very interesting question. Okay, so the answer is it all depends on the ant's will. So if ant because you have seen when ants are walking on let's say mm, some plate or something, and you shut them off, but they are not moving a bit, they will just hold on to the plate. Do you remember those times? So actually this is also something like that. So to explain the physics part of it, why the ants will is important in this type of question is, first we have to look at what the degree of freedom is and what actually is happening. Okay, right now the system is and working straight line on a disk, so we won't worry about the disk. We'll just take 2 points being A and B, and there's a straight line, and ant is walking there. Let me draw that ant. So this ant is walking like this. I don't know if walking with 6 legs is called walking. Oh, okay, sorry. We just destroyed our ant. So this is our ant, and let's see, it is rotating, and now ant is moving from here to here, right? So what will happen, we will look at this ant, how much force it is experiencing. So let's take out this ant somewhere else. Now we are that ant. Okay, let's say this ant has a mass m, and what type of forces it would be carrying is m, the mass of the ant. So there will be two force component, one in radial direction and one in a tangential direction. So radial direction, the force will be m omega square r. Okay, here omega and r are both changing with time. We know that omega is changing as this, and r, exactly we don't know how this r is changing, because in that disk, if you will see, r at this point, let's say in this figure, r at this point is same as r at that point, b point. Okay, but in middle it won't be same. Okay, so r1 is nearly equal to r2, but r3 is not equal to r1. Okay, so we cannot say anything about r, but the thing is they will be near to one value. So but what the impression is that omega is increasing and omega square also will be increasing, so hence this radial force will slowly increase into very high account. So what will happen, the cat will kind of fling, okay, it's up to its will to withstand this force by providing a stickiness from its feet or its limbs. So this is half question solved. There is a tangential force also, which is equal to m alpha r. This is also some force, and let's look at the direction part of it. So the radial will be just outwards, this fr will be like this, and the other f tangential will be back side, because the disc is rotating in this direction, so the rotation, the force will be in the back side. And what actually does it do is, since it had to reach from point A to B, it is getting pushed in back side. So first it had to withstand that force, and then it has to provide additional force to reach to point B. So the story is very tough for this end. And here what is happening, that as it is moving from point A to B, the situation is getting more tough and tough, because this will be the radial resultant force by parallelogram rule, F resultant, and then the friction force, and had to provide in the opposite direction. So this is will, and will. So if this question is asked in very textbook form, then the answer is 1, because it has go from point A to B, so it's a straight line, so that's the degree of freedom. But if it's asked, keep practical scenario into mind, so then you have to think about these stuff, okay, because this is what makes you a more practical point of view. So it had to withstand both of these forces. If it didn't, it will be just flung out of the system, and then that's a different problem altogether now, because it's like ant is flying. Now what will be the degree of freedom? Okay. So the answer is depends on the ant's will. Alright, now moving to the next question. Question number 3. So read the question. So there is a uniform disc, and that is stationary for now, okay, but it can roll without slipping on a horizontal line as shown in the figure. Now this disc has a short axle of negligible mass and radius, and from this axle is a suspended a simple pendulum, okay. So there is a pendulum on a, let's say, a very large wheel, and the length of this pendulum is less than the radius of this disc. Now we have to find the degree of freedom. Determine the degree of freedom as well as constraint to describe the motion of the ball. So first of all, how many degree of freedom was required to describe the motion? By the way, any doubt in the last question? Okay, I will take your silence as yes. No doubt. Yes, no doubt. Okay, so moving on to question number 3. Here again it's a similar question. Now here no will is there because everything is non-living. So here what is happening that this theta naught, if it's disturbed, if this mass is disturbed, what will happen? This mass will go in this direction and then it will come back. Okay, but this going and coming back will give some rotation to this bigger mass. Alright, so that is the whole page. So I will write this solution here itself. So it is 1 degree of freedom problem, and let's say that degree of freedom is theta naught, which is angle made by the pendulum from a horizontal. Okay, so but what about the other rotation? So let phi be that now how to find that constraint equation? So it can be either found by mass balance, where we balance the moment of inertia, like how much rotation it is caused, or we can go by energy balance. So in energy balance, what will happen? Kinetic energy is equal to potential energy. Kinetic energy terms are half ml square I of the disk r square into r square will come into id only. So this is the constraint equation. This complete our question number 3. Now moving on to question number 4. So here a ball is rolling without slipping inside a ball B which is rolling without slipping on the rigid beam. The rigid beam is free to sway on the side, and the ball is given position. Uh, Ball is at the given position. It is given a initial tangential velocity v naught. So again, the question is, what are the degree of freedom required to describe the motion of the ball? So you have to think practically in this also. Okay, so there is a jhula and it can swing sideways. Okay, this can go like this and that side also. And then there is already have made okay. Then there is this ball. Some cutting shading. Okay, so this is the ball. We have to change to dotted line and also group it. And there is one more ball called A. initially what was at this point, and now it is here. Let's say this is the another edge. This is A, this is B, and let's draw this whole scenario. Okay. So first of all, the first case will be where this A, the velocity is given is so high that it flings off. Okay. So it's like at this point, at this C point, let's take this point as C, it releases itself into a projectile. Now there can be two things. When the speed is not so great, so what will happen in that, it will just drop at this point after having a projectile, and then from here it can go anyway like this or that side. So it depends on the properties of the collision, but if it's high enough, then it can go down also. Okay, so two type of projectile. Let's say projectile 1, projectile 2. The second, which is most common case where in the textbook, is when V0 is small so that the system vibrates. Okay, so it will go up to this point and then it will come back. It will go up to this point and then it will come back. Okay, so it describes all the cases. So this covers our abstraction part. Today we learned about abstraction. And now we will be back to the questions what we are doing in the previous class. So this is question 4. So we will start question 5. Okay, so I'm taking 5-minute break. Up till that time you can read the question and also the strategy. So it is based on impulse and momentum question now. Okay, so in this question we have an automobile is weighing 1800 kg is driven down a 5-degree incline at speed of 100 km per hour when the brakes are applied, causing a constant total braking force of 7000 Newton. We have to determine the time required for the automobile to come to a stop. So we have to apply principle of impulse and momentum, and the impulse is equal to the product of the constant force and the time interval. Okay, so applying the principle of impulse and momentum, mv1 is equal to, or mv1 plus summation of impulse from point 1 to 2 is equal to mv2. Now taking components parallel to incline, mv1 plus mg sine 5 degree, therefore the figure ft is equal to 0. So we have 100 km per hour, right? So this is going at 100 km per hour. And so 100 per hour, we have to convert it into meter per second. So 1000 meter multiplied 300 second. So this comes out to be 8 meter per second. V1 is 27.78 plus 1800 into 9.81 sine 5 degree over t will be also there. Where the impulse now. Minus 7000, that is also t, I think, f t into t So this will give us t is equal to 9.16 second. So this much time to deaccelerate from 0 to 100 to 100 km per hour to 0. Now point to be noted in this question are we can use Newton's second law or by FPT to solve this problem. First we would determine the cause deacceleration. Then we have to separate variables. And then integrate. So it can relate the velocity, acceleration, in this case deacceleration, and time. Now next is question number 5. An automobile of mass 1000 kg is driven down a 5-degree incline at a speed of 72 km per hour when the brakes are applied, causing a constant total braking force of 5000 Newton. Now determine the distance traveled by the automobile as it comes to the stop. So now strategy is to evaluate the change in kinetic energy and then determine the distance required for the work to equal the kinetic energy change. We'll go step by step. So first step is evaluate the change in kinetic energy. So let's see what is happening. So let's say it has moved up to x meters. So V1 is 72 km per hour. Let's quickly change the units. So 72 km per hour means into 1000 into 1 kilometer to 1 hour by 3600 seconds. So this will be 20 meter per second. Now T1, finding T1 is equal to half mv1 square, which is equal to half 1000 kg Okay, so in this question we have so now strategy is to evaluate the change in kinetic energy and then determine the distance required for the work to equal the kinetic energy change. We'll go step by step. So first step is evaluate the change in kinetic energy. So let's see what is happening. So let's say it has moved up to x meters. So V1 is 72 km per hour. Let's quickly change the units. So 72 km per hour means into 1000 meter by 1 kilometer to 1 hour by 3600 seconds. So this will be 20 meter per second. Now T1, finding T1 is equal to half mv1 square, which is equal to half 1000 kg into 20 meter per second square two lakh joule. Now since V2 is 0, hence T2 is also 0. Now finding the distance required for the work to equal the kinetic energy change. For that we have to find U from 1 to 2. So here we have to find the force. Okay, so force comes out to be minus 5000 Newton into X plus 1000 kgs into small g into sine 5 degrees. I think I should write small. No, this is okay. Into X. Balancing the equations, T1 plus U1 to 2 is equal to T2, hence X, so 2, 1, 2, 3, 4, 2 lakh joules is equal to 4145 Newton to X आप ऑफिस जाएंगे क्या? अच्छा अच्छा ओके. So this gives us X is equal to 48.3 meter. So that was the distance required for the work to equal the kinetic energy change. Now let's have a little bit of thinking. Try to solve this question using Newton's law. You would require like determining the car's deceleration from the FBD and then integrating this to use the given velocity formation. So that is one way, and another way is by using momentum conservation. So that will be looking after half of the class, and using the Using the principle of work of energy, it also allows you to avoid that calculation. So let me write it down. Solving this problem using Newton's second law would require determining the cause deceleration from the free body diagram. And then integrating so this is insight 1. Okay, moving on to the next question. So two blocks are joined by an inextensible cable as shown. If the system is released from rest, determine the velocity of the block A after it has moved 2 meter. Assume that the coefficient of the friction between block A and the plane is mk, which is equal to 0.25, and that of the pulley is weightless and frictionless. So again, the strategy is to apply the principle of work and energy, separating to the block A and B. Then when the two relations are combined, the work of the cable force cancel, and then we can solve for the velocity. So first is modeling and analysis, and we are applying the principle of work and energy separately to block A and B. Now this is the figure. First block A, So this gives us 490 Newton. Now we don't know what the velocity is, so we'll apply principle of work and energy, but we know it started from the rest, so T1 is 0. Then U12 has two components to it. Can you mute yourself? Thank you. Okay, so yes, yes, Samarji, you have some doubt? So this potential energy will have two terms because two masses are moving, hence like this. And now WB can you please mute yourself? So when these two relations are combined, the work of the cable force is cancelled, and now we can solve for the velocity. So let's do that. this will give the two equations. We can sum them up. So these will cancel out. Now everything will be in V. And upon solving, V comes out to be 4.43 meter per second. Now here we have individually applied energy conservation into block A and block B, but we can also combine energy, and then there won't be any use of FC, but actually this FC is the tension force, so hence it's a constraint force. To find this constraint force, we had to take individual value. So if you have to save time and you don't need a constraint force, knowledge of the constraint force, then you can use for the whole system and there won't be any issue. Okay, moving to the next question. Question 7. So here a spring is used to stop a 60 kg package which is sliding on the horizontal surface. This spring has the constant K, and it is held by the cable so that it is initially compressed to 120 mm. Now this package has the velocity of 2.5 meter per second in the position shown, and the maximum deflection of the spring is 40 mm. Now first we have to determine the coefficient of kinetic friction between the package and the surface, and B, we have to find the velocity of the package as it passes again through the position shown. So the package is getting bound by this spring arrangement. So here our strategy will be apply the principle of work and energy between the initial position and the position at which the spring is fully compressed and the velocity is 0. The only unknown in the relation is the frictional coefficient, because distance we know that it will go up to 40 mm, and the distance from this package from this point to that spring arrangement, that is also known. The only unknown will be coefficient of friction. Next we can apply the principle of work and energy for the rebound of this package, and the only unknown in this relationship will be velocity at the final position. Moving to the first part. Initial kinetic energy comes out to be 187.5 joule, and final kinetic energy when it stops for an instant, then it's 0. Now if you find the potential energy for the work done, we find the work done from 1 to 2 by the force of friction mu k is our unknown, normal force is this is equal to since mu k is dimensionless, Now applying the area of the trapezoid formula, we can find the work done by the spring. Delta x is known. Work done from moving from one point to 2 point is given by the friction force plus the spring, work done by the spring. Applying the formula, the energy conservation. Since T2 is 0, only we have to take care of T1, which is we have already found out in the starting. So this gives us our new K. .2. That is our solution. Now that this is the only one part. Now for the second part, we know that T2 is 0, but we are going to now T3. And now in T3, V3 is unknown. And the potential energy from 2 to 3 is again either by the friction force or spring force. So we know the value of mu, so now applying the energy conservation for the second time. gives our solution V3 is equal to 1.103 meter per second. So here we needed to break this problem into two segments, and from the first segment we were able to determine the coefficient of friction, and then we could use principle of work and energy to determine the velocity of the packet at the same location, but at first location only, but now it's coming from the different side. So point to be noted are the system does not lose any energy due to the spring, and it returns all of its energy back to the package. Now we would need something else if we need some absorption of the energy. Those are called dampers, and we will be visiting it in the next part of the course. Moving to the next question numbers 7, 8. So a 1000 kg car starts from the rest from point A as shown in the figure, and it moves without friction down the track as shown. Determine first the force exerted by the track on the car at point 2, which is the lowest of the datum, and B, the minimum safe value of the radius of the curvature at point 3. So again, this strategy is to apply the principle of work and energy to determine the velocity at point 2. Then applying Newton's second law to find normal force by the track at the point 2. Then applying principle of work and energy to determine the velocity at point 3. Then applying Newton's second law to find minimum radius of curvature at point 3, such that a positive normal force is exerted by the track, otherwise it will fly off. So it's similar to the previous question, 3 points, and we have to apply principle of work and energy 2 times. Since it started with rest, so T1 is equal to 0. Work done from point 1 to 2 is positive. first task is done. We found out the velocity at the point 2. So A part is done. For B part, you have to apply Newton's second law. N is equal to 5W. So W is our weight here. Now the third for B part. So V3 comes out to be 12.13 meter per second. So applying the tandem of Newton's second law now. So we have used both formulas there. So this gives us the value of rho 3, which is equal to 15 meter. So in this example, we needed both Newton's second law and principle of work and energy. Work energy is used to determine the speed of the car, and Newton's second law is used to determine the normal force. One thing which you can also do is you can provide from 1 and 2, you can take the force of the normal force, and then you can apply energy theorem, energy equation at that point also.